For all those who are too busy to read fat books, yet nonetheless seek a conduit to the cosmos. Preface. In recent years, no more than a week goes by without news of a cosmic discovery worthy of banner headlines. While media gatekeepers may have developed an interest in the universe, this rise in coverage likely comes from a genuine increase in the public's appetite for science. Evidence for this abounds, from hit television shows inspired or informed by science, to the success of science fiction films starring marquee actors and brought to the screen by celebrated producers and directors. And lately, theatrical release biopics featuring important scientists have become a genre unto itself. There's also widespread interest around the world in science festivals, science fiction conventions, and science documentaries for television. The highest-grossing film of all time is by a famous director who set a story on a planet orbiting a distant star. And it features a famous actress who plays an astrobiologist. While most branches of science have ascended in this era, the field of astrophysics persistently rises to the top. I think I know why. At one time or another, every one of us has looked up at the night sky and wondered, what does it all mean? How does it all work? And what is my place in the universe? If you're too busy to absorb the cosmos via classes, textbooks, or documentaries, and you nonetheless seek a brief but meaningful introduction to the field, I offer you Astrophysics for People in a Hurry. If I've succeeded, you'll be culturally conversant in my field of expertise, and you just may be hungry for more. The universe is under no obligation to make sense to you. The world has persisted many a long year, having once been set going into the appropriate motions. From these, everything else follows. Lucretius, 50 BC. In the beginning, nearly 14 billion years ago, all the space and all the matter and all the energy of the known universe was contained in a volume less than 1/trillionth the size of the period that ends this sentence. Conditions were so hot, the basic forces of nature that collectively described the universe were unified. Though still unknown how it came into existence, this sub-pinpoint-sized cosmos could only expand rapidly in what today we call the Big Bang. Einstein's general theory of relativity, put forth in 1916, gives us our modern understanding of gravity, in which the presence of matter and energy curves the fabric of space and time surrounding it. In the 1920s, quantum mechanics would be discovered, providing our modern account of all that is small: molecules, atoms, and subatomic particles. But these two understandings of nature are formally incompatible with one another, which set physicists off on a race to blend the theory of the small with the theory of the large into a single coherent theory of quantum gravity. Although we haven't yet reached the finish line, we know exactly where the high hurdles are. One of them is during the Planck era of the early universe. That's the interval of time from t equals 0 up to t equals 10 to the minus 43 seconds. 1/10 million trillion trillionths of a second after the beginning. And before the universe grew to 10 to the minus 35 meters, 100 billion trillion trillionths of a meter across. The German physicist Max Planck, after whom these unimaginably small quantities are named, introduced the idea of quantized energy in 1900 and is generally credited as the father of quantum mechanics. The clash between gravity and quantum mechanics poses no practical problem for the contemporary universe. Astrophysicists apply the tenets and tools of general relativity and quantum mechanics to very different classes of problems. But in the beginning, during the Planck era, the large was small, and we suspect there must have been a kind of shotgun wedding between the two. Alas, the vows exchanged during that ceremony continue to elude us, and so no known laws of physics describe with any confidence the behavior of the universe over that time. We nonetheless expect that by the end of the Planck era, gravity wriggled loose from the other still unified forces of nature, achieving an independent identity nicely described by our current theories. As the universe aged through 10 to the minus 35 seconds, it continued to expand, diluting all concentrations of energy, and what remained of the unified forces split into the electroweak and the strong nuclear forces. Later still, the electroweak force split into the electromagnetic and the weak nuclear forces, laying bare the four distinct forces we have come to know and love, with the weak force controlling radioactive decay, the strong force binding the atomic nucleus, the electromagnetic force binding molecules, and gravity binding bulk matter. A trillionth of a second has passed since the beginning. All the while, the interplay of matter in the form of subatomic particles and energy in the form of photons, massless vessels of light energy that are as much waves as they are particles, was incessant. The universe was hot enough for these photons to spontaneously convert their energy into matter-antimatter particle pairs, which immediately thereafter annihilate, returning their energy back to photons. Yes, antimatter is real, and we discovered it, not science fiction writers. These transmogrifications are entirely prescribed by Einstein's most famous equation, E equals mc squared, which is a two-way recipe for how much matter your energy is worth and how much energy your matter is worth. The c squared is the speed of light squared, a huge number which, when multiplied by the mass, reminds us how much energy you actually get in this exercise. Shortly before, during, and after the strong and electroweak forces parted company, the universe was a seething soup of quarks, leptons, and their antimatter siblings, along with bosons, the particles that enable their interactions. None of these particle families is thought to be divisible into anything smaller or more basic, though each comes in several varieties. The ordinary photon is a member of the boson family. The leptons most familiar to the non-physicist are the electron and perhaps the neutrino. And the most familiar quarks are, well, there are no familiar quarks. Each of their 6 subspecies has been assigned an abstract name that serves no real philological, philosophical, or pedagogical purpose, except to distinguish it from others. Up and down, strange and charmed, and top and bottom. Bosons, by the way, are named for the Indian scientist Satyendra Nath Bose. The word lepton derives from the Greek leptos, meaning light or small. Quark, however, has a literary and far more imaginative origin. The physicist Murray Gell-Mann, who in 1964 proposed the existence of quarks as the internal constituents of neutrons and protons, and who, at the time, thought the quark family had only 3 members, drew the name from a characteristically elusive line in James Joyce's Finnegan's Wake. 3 quarks for Muster Mark. One thing quarks do have going for them: all their names are simple. Something chemists, biologists, and especially geologists seem incapable of achieving when naming their own stuff. Quarks are quirky beasts. Unlike protons, each with an electric charge of +1, and electrons with a charge of -1, quarks have fractional charges that come in thirds. And you'll never catch a quark all by itself. It will always be clutching other quarks nearby. In fact, the force that keeps 2 or more of them together actually grows stronger the more you separate them, as if they were attached by some sort of subnuclear rubber band. Separate the quarks enough, the rubber band snaps, and the stored energy summons E equals mc squared to create a new quark at each end, leaving you back where you started. During the quark-lepton era, the universe was dense enough for the average separation between unattached quarks to rival the separation between attached quarks. Under those conditions, allegiance between adjacent quarks could not be unambiguously established, and they moved freely among themselves, in spite of being collectively bound to one another. The discovery of this state of matter, a kind of quark cauldron, was reported for the first time in 2002 by a team of physicists at the Brookhaven National Laboratories, Long Island, New York. Strong theoretical evidence suggests that an episode in the very early universe, perhaps during one of the force splits, endowed the universe with a remarkable asymmetry, in which particles of matter barely outnumbered particles of antimatter by about 1,000,000,001 to 1,000,000,000. That small difference in population would hardly get noticed by anybody amid the continuous creation, annihilation, and recreation of quarks and antiquarks, electrons and anti-electrons, better known as positrons, and neutrinos and antineutrinos. The odd man out had oodles of opportunity to find somebody to annihilate with, and so did everybody else. But not for much longer. As the cosmos continued to expand and cool, growing larger than the size of our solar system, the temperature dropped rapidly below 1,000,000,000,000 degrees Kelvin. A millionth of a second has passed since the beginning. This tepid universe was no longer hot enough or dense enough to cook quarks, and so they all grabbed dance partners, creating a permanent new family of heavy particles called hadrons, from the Greek hadros, meaning thick. That quark to hadron transition soon resulted in the emergence of protons and neutrons, as well as other less familiar heavy particles, all composed of various combinations of quark species. In Switzerland, back on Earth, the European Particle Physics Collaboration, CERN, uses a large accelerator to collide beams of hadrons in an attempt to recreate these very conditions. This largest machine in the world is sensibly called the Large Hadron Collider. The slight matter-antimatter asymmetry afflicting the quark-lepton soup now passed to the hadrons, but with extraordinary consequences. As the universe continued to cool, the amount of energy available for the spontaneous creation of basic particles dropped. During the hadron era, ambient photons could no longer invoke E equals mc squared to manufacture quark-antiquark pairs. Not only that, the photons that emerged from all the remaining annihilations lost energy to the ever-expanding universe, dropping below the threshold required to create hadron-antihadron pairs. For every billion annihilations, leaving 1,000,000,000 photons in their wake, a single hadron survived. Those loners would get to have all the fun, serving as the ultimate source of matter to create galaxies, stars, planets, and petunias. Without the 1,000,001 to 1,000,000,000 imbalance between matter and antimatter, all mass in the universe would have self-annihilated, leaving a cosmos made of photons and nothing else. The ultimate let there be light scenario. By now, 1 second of time has passed. The universe has grown to a few light years across, about the distance from the sun to its closest neighboring stars. At 1,000,000,000 degrees, it's still plenty hot and still able to cook electrons, which, along with their positron counterparts, continue to pop in and out of existence. But in the ever-expanding, ever-cooling universe, their days, seconds really, are numbered. What was true for quarks and true for hadrons had become true for electrons. Eventually, only one electron in 1,000,000,000 survives. The rest annihilate with positrons, their antimatter sidekicks, in a sea of photons. Right about now, one electron for every proton has been frozen into existence. As the cosmos continues to cool, dropping below 100,000,000 degrees, protons fuse with other protons as well as with neutrons, forming atomic nuclei and hatching a universe in which 90% of these nuclei are hydrogen and 10% are helium, along with trace amounts of deuterium, heavy hydrogen, tritium, even heavier hydrogen, and lithium. 2 minutes have now passed since the beginning. For another 380,000 years, not much will happen to our particle soup. Throughout these millennia, the temperature remains hot enough for electrons to roam free among the photons, batting them to and fro as they interact with one another. But this freedom comes to an abrupt end when the temperature of the universe falls below 3,000 degrees Kelvin, about half the temperature of the sun's surface, and all the free electrons combine with nuclei. The marriage leaves behind a ubiquitous bath of visible light, forever imprinting the sky with a record of where all the matter was in that moment, and completing the formation of particles and atoms in the primordial universe. For the first billion years, the universe continued to expand and cool as matter gravitated into the massive concentrations we call galaxies. Nearly 100 billion of them formed, each containing hundreds of billions of stars that undergo thermonuclear fusion in their cores. Those stars, with more than about 10 times the mass of the Sun, achieve sufficient pressure and temperature in their cores to manufacture dozens of elements heavier than hydrogen, including those that compose planets and whatever life may thrive upon them. These elements would be stunningly useless were they to remain where they formed, but high-mass stars fortuitously explode, scattering their chemically enriched guts throughout the galaxy. After 9 billion years of such enrichment in an undistinguished part of the universe, the outskirts of the Virgo supercluster, in an undistinguished galaxy, the Milky Way, in an undistinguished region, the Orion Arm, an undistinguished star, the Sun, was born. The gas cloud from which the Sun formed contained a sufficient supply of heavy elements to coalesce and spawn a complex inventory of orbiting objects that includes several rocky and gaseous planets, hundreds of thousands of asteroids, and billions of comets. For the first several 100 million years, large quantities of leftover debris in wayward orbits would accrete onto larger bodies. This occurred in the form of high-speed, high-energy impacts, which rendered molten the surfaces of the rocky planets, preventing the formation of complex molecules. As less and less accretable matter remained in the solar system, planet surfaces began to cool. The one we call Earth formed in a kind of Goldilocks zone around the Sun, where oceans remain largely in liquid form. Had Earth been much closer to the Sun, the oceans would have evaporated. Had Earth been much farther away, the oceans would have frozen. In either case, life as we know it would not have evolved. Within the chemically rich liquid oceans, by a mechanism yet to be discovered, organic molecules transitioned to self-replicating life. Dominant in this primordial soup were simple anaerobic bacteria, life that thrives in oxygen-empty environments, but excretes chemically potent oxygen as one of its byproducts. These early single-celled organisms unwittingly transformed Earth's carbon dioxide-rich atmosphere into one with sufficient oxygen to allow aerobic organisms to emerge and dominate the oceans and land. These same oxygen atoms, normally found in pairs, O2, also combined in threes to form ozone, O3, in the upper atmosphere, which serves as a shield that protects Earth's surface from most of the Sun's molecule-hostile ultraviolet photons. We owe the remarkable diversity of life on Earth, and we presume elsewhere in the universe, to the cosmic abundance of carbon and the countless number of simple and complex molecules that contain it. There is no doubt about it, more varieties of carbon-based molecules exist than all other kinds of molecules combined. But life is fragile. Earth's occasional encounters with large, wayward comets and asteroids, a formerly common event, wreaks intermittent havoc upon our ecosystem. A mere 65 million years ago, less than 2% of Earth's past, a 10 trillion-ton asteroid hit what is now the Yucatan Peninsula and obliterated more than 70% of Earth's flora and fauna, including all the famous outsized dinosaurs. Extinction. This ecological catastrophe enabled our mammal ancestors to fill freshly vacant niches rather than continue to serve as hors d'oeuvres for T-Rex. One big-brained branch of these mammals, that which we call primates, evolved a genus and species, Homo sapiens, with sufficient intelligence to invent methods and tools of science and to deduce the origin and evolution of the universe.